Hi, my name is Bailey Steen, and I'll be presenting my research on the preparation of macrocyclic polyphenylethynylarene ethers. Before getting into the synthesis of these molecules, it's important to talk about the significance of conjugation and resonance. According to the molecular orbital theory, pi bonds are formed when two parallel p orbitals overlap. Conjugation is an overlapping of two p orbitals that allows for the sharing of pi electrons across a sigma bond. A conjugated system is a series of alternating sigma bonds and pi bonds in which the p orbitals are aligned, which is exhibited in the illustration on the left. The pi electrons will then delocalize and share among a group of atoms, which is a property we refer to as resonance. Resonance creates stability and a lower energy state within a molecule. Conjugated molecules exhibit interesting qualities, one of them being their increase in light absorption. Large conjugated molecules with extended pi systems allow for a large absorption across a wide range of the visible spectrum, which is located in the 400 nanometer to 750 nanometer range. As conjugation increases, wavelength increases. Higher conjugation causes the closing of the HOMO-LUMO gap, and it takes less energy to excite electrons. So this information on conjugation and resonance begs the question, what's the purpose behind wanting to synthesize molecules with high conjugation? And the answer to that is in the light harvesting properties these highly conjugated molecules possess. Some examples include solar cells and photoreactive materials like organic light-emitting diodes, like those found in flat-screen televisions. There's two types of conjugated systems that fit these parameters, and they include polymers and dendrimers. Polymers don't always involve a termination reaction, and their purity is low, due to the synthesis of multiple non-isolated compounds of varying lengths. On the other hand, the synthesis of dendrimers requires multiple specific steps with purification in between each step, and purity is high, due to the purposeful synthesis of a structurally specific isolated compound. Moreover, conjugated dendrimers contain extended pi electron systems, which allows for the large absorption across a wide range of the visible spectrum, which carries into creating smaller HOMO-LUMO gaps along the conjugated chains. Dendrimers are defined as highly branched, symmetrical, monodispersed macromolecules that have compact three-dimensional spherical shapes. Their property of being monodispersive simply means that they are polymers composed of molecules of the same mass. Their structure consists of a central core, branching units, which create internal cavities, and surface groups. Typically, surface groups aren't linked together or cyclized, which contributes to their spherical shape, and single bonds around the core also contribute to this spherical nature. Since dendrimers have a large amount of conjugation, they can be used for the innovation of electronic and photonic applications like organic LEDs and solar cells. The problem with the conventional dendrimer is the efficiency of the intramolecular energy transfer decreases with increasing dendrimer size. This decrease in energy transfer is due to the twisting around the single bonds of dendrons, which results in a loss of conjugation, which reduces the light harvesting properties in the entire molecule. This research is centered around the synthesis of a spiderweb dendrimer. These are different than the conventionally accepted dendrimer as they are flat, two-dimensional structures with an extended pi conjugated system. We're trying to make them flat and rigid so the dendrimer can maintain its high conjugation without twisting up to form that spherical shape. This can be done by tying the branching units together through ether linkages, which prevents rotation around the single bonds. Dendrimers can be synthesized in a series of stepwise and repetitive reactions from synthetic branched monomer units which radiate from a core molecule. Since such large molecules are often difficult to work with, and we don't know exactly how certain reactions will go, we can use model compounds to test out different methods to see how things work, and when we find specific procedures that work and produce good yields, we can use those methods to continue the process of expanding the dendrimer. So our starting material is 3-hydroxybenzaldehyde, and from the NMR spectra we can see the aldehyde proton, the alcohol proton, and the aromatic protons. Getting into the mechanism, we start with the protection of the alcohol. Tert-butyl dimethyl silyl chloride will react with an alcohol in the presence of a weakly basic aromatic amine and under microwave conditions without a solvent. This forms a silyl ether. This reaction was run under argon to prevent the TBDMS from reacting with atmospheric moisture. Purification was achieved via silica gel column chromatography and the yield was 84%. This is an NMR spectra of the purified protected aldehyde. We can see the alcohol proton is now gone, and we can see the aromatic protons much clearer. The protons from the protecting group are also present. The reaction was continued by the formation of an ylide by carbon tetrabromide, triphenylphosphine, and zinc. A Wittig reaction then creates the alkene dibromide. This was purified by silica gel column chromatography, and the yield was 97%. This is an NMR spectra of the purified protected alkene compound. We can see the aldehyde proton has disappeared, and the proton from the alkene near the halogens is now present. The reaction proceeds with N-butyl lithium, which is a very strong base that is flammable when exposed to atmospheric moisture, so the reaction is run under argon with dry glassware and anhydrous solvents. We also ran the experiment at -20°C to reduce the reactivity of the base. Saturated ammonium chloride was added to neutralize any remaining lithium, and we extracted with hexanes. The product of this step of the reaction is one of our key intermediates, and the yield was 90%. This is an NMR spectra of the pure protected alkyne. Here we can see that the alkene proton near the halogens is gone, and the terminal alkyne proton is now present. The reaction continues with the terminal alkyne and the diiodo compound in the presence of a palladium and a copper catalyst, with triethylamine acting as a base and a solvent. The reaction was conducted under argon because palladium is unstable in the presence of oxygen. We did run into a couple of hiccups with this reaction. We ran it on too large of a scale, so the magnetic stir bars we were using weren't sufficient for the amount of viscous liquid we had to work with, so we had a poorer yield due to the lack of mixing. The product was also purified by silica gel column chromatography, and the yield was 45%. This is an NMR of the purified protected diene. Here we can see the terminal alkyne proton is gone, and all that's left are the aromatic protons and the protecting group protons. It should be noted that the integration for the aromatic protons here is much greater because we've got 2 more phenylerenes attached. We have successfully synthesized and characterized the key molecule that will be used to prepare the variety of highly conjugated organic macrocycles. Once the model systems have been fully studied and the reaction conditions optimized, synthesis of the first flat dendrimer will begin. We continue by using a fluoride ion source. We chose tetrabutyl ammonium fluoride. This reaction is complete, but we are currently working on purifying the product. Once we purify and verify through NMR spectroscopy that we are indeed working with the product that we intend to work with, we can continue on to the cyclization, which will give us the monomacrocycle. Potassium carbonate will deprotonate the alcohols, and an SN2 reaction will occur, which will form the ether linkages that aid in solubility. This is just a summary of the results from each individual reaction. The protection of the alcohol gave an 84% yield. From aldehyde to alkene, we had a 97% yield. Alkene to terminal alkyne was a 90% yield, and the terminal alkyne to the diene was a 45% yield. I just want to take a moment to acknowledge my research advisor, Dr. Selby, for his mentoring and guidance and for giving me the opportunity to participate in this research. The Mississippi College Department of Chemistry and Biochemistry, and co-workers in my research group, Netta and River, for their advice, assistance, and patience with me. And these are my references. Thank you.